Good morning. This is Christina Long and this is the Science 411. Today's video is on writing equilibrium expressions. So what we're doing here is we're basically taking an equation and we are breaking it down and putting it into something called a concentration constant. And so what you're looking for here is in this main equation, this is your generalized equation. Alright, and there are ways to break this down. Number one, this K stands for constant. I have to spell constant right, but that's okay. So I've got constant here, and that subscript C, that means that you're dealing with concentration. And there are different constants out there, so it's important to pay attention to your subscript. The stuff in the molarity brackets, the capital letters, that's basically, it's telling you, because it's in the molarity brackets, you're dealing with molarity of your different substances. And then your coefficients are shown in your exponents there. So these are coefficients used in the balanced equation. Now there are a couple of things that you need to pay attention to here. You've got your basic equation set up in the purple, in the box. And I've kind of broken down the setup of how this is done below. But if you notice, your products go on the top of the equation, or top of the fraction. So in your numerator, your products show up, and then your reactants show up in the denominator. And another thing to pay attention to is in the equation, you're adding things together. But in this constant or the equilibrium expression, the plus sign changes to a multiplication sign. And there's one last thing to note, and it's kind of a cautionary thing, but you do not use solids or liquids when you're writing these expressions. And I'll show you some examples here in just a second. A couple more things to look at. Again, the Kc stands for the concentration constant, but there's something else called a Kp, which is a pressure constant. You're only going to use gas, which is a lowercase g, and aqueous, AQ, in writing these constants. So you're going to ignore your solids and you're going to ignore your liquids. It is worth noting that gases use both the Kc and the Kp expressions, and that's really the only one that's going to use both. So in this equation, you've got a balanced equation, and that's important that you've got to have a balanced equation when you begin all this. And if you remember, what we're doing is we're taking the products first. So we're looking at all these states of matter. I've got gases in all three, so we're good to go. So I'm going to end up making a Kc and a Kp, but we're going to start with the Kc, or the concentration constant. And I'm going to start with my products on top, and I'm going to put NH3 in a bracket, in a molarity bracket, and then I'm going to take that 2 and I'm going to make it an exponent. And then I'm going to put my reactants in the denominator. So I have 1 mole of NH2, and since it's 1 mole, I don't need to put anything after it as an exponent. And then I'm going to multiply it, not add it, but multiply it, times my next substance, which is H2. And I'm going to put that in the bracket, and since my coefficient is a 3, I'm going to put an exponent of 3 there. And so that's my Kc value of this equation. And because I'm dealing with gases, excuse me, I'm going to write a Kp as well. Now this is going to be similar, but not totally the same. Because this is pressure, I'm still going to follow the same format, but it's going to look a little bit different. I'm going to put pressure for the gas over on the right, the NH3, and I'm going to use the P there, and that's where I'm going to put that exponent, or the coefficient as an exponent. So I'm going to put P2, and then down below I'm going to recognize what gas it was. And then I'm going to follow the same format as my Kc, and since I only had a coefficient of 1 for my N2, I'm going to put P with my N2 down at the bottom there to show what it is. And then I'm going to put P3 because I had a coefficient of H2. And that is how we're writing the pressure constant for that particular equation. So you've got two different equations. They're very, very similar, but they have a little bit different look depending on what they're being used for. In this next equation, I'm looking at my states of matter, and I have two solids and a gas. And so I'm not going to be dealing with the solids. I don't do anything to them, I just ignore them. And because I am dealing with a gas, I can write a Kc and a Kp. And in this case, the only thing that I have to deal with is that CO2, so it's just going to be Kc equals my CO2, and for the Kp, or the constant, or the pressure constant, it's going to be not a K, but it's going to be a P with a CO2. And since there's no coefficient, I don't have an exponent for that P. Seems simple enough. So we've got another equation here. So we look and we have a solid, aqueous, aqueous, and solid. You don't have any gases there, so you're looking at just a Kc, and again we ignore our solids. So we are going to start with our products and our aqueous, and essentially you can ignore the copper and the silver as far as the solid forms. On the right hand side I have a +2 copper cation, and I'm going to put it over a silver cation, and because I've got this coefficient of 2, I'm going to put a 2 there as my exponent. So that's my constant for that particular equation. In our last equation, we have a gas and we have two aqueous solutions. So we're going to use all three there, which is nice, or both of your, you're going to use all three of your specimens, and then we're going to actually write two expressions, one Kc and one Kp, and we're writing the Kp because, well, you've got a gas there. So we're going to again start with our products. So for our concentration, it's going to be NaHCO3 over our CO2 times our NaOH. And that's all we have to do for our Kc. And our Kp is going to look very, very similar, but we're still going to put our NaHCO3 in brackets because it's an aqueous solution. The question is what do we do with our gas now in that Kp? Well, remember, there's no coefficient there. So that means that my pressure is just times 1, or it's to the first power. So I'm going to put pressure there and CO2 and still multiply it by the concentration of NaOH. Now something that's important to notice here in this particular thing, and you've seen it before as well, but in these two expressions, you've got your aqueous and then you've got your gas. And it looks all the same with your Kc, but with your Kp it definitely does not. And something that's going to be important for you to realize is that there are two new terms, and it's not super new, but it's new for this particular topic. You've got homogeneous and heterogeneous equations. And homogeneous or homogeneous just means it's the same state of matter throughout. So this particular equation is not homogeneous or homogeneous. It's not the same state of matter throughout. It in fact is heterogeneous, and it's because it contains different states of matter. Because you've got, in this case, a gas and two aqueous, it's going to be heterogeneous. So when you go back and take a look at the other ones, if I had to classify these, when you're looking at them, you're going to end up, the expression here is going to be homogeneous. And the reason is because you're only dealing with the two aqueous. In this case, it would definitely be homogeneous because it's just got the gas. And then over here, with your N2 plus 3H2 yields 2NH3, the production of ammonia, that is going to be homogeneous as well. So, that's how you write the general equilibrium expressions for concentration and for pressure. We'll be dealing with this more in our next example, but it's important that you be able to write the expressions, and then in the next video we'll take the expressions and then we will go ahead and add some numbers to it so you can go ahead and find the actual values for Kc and Kp. But until then, have a great day.